Hello, Miss. This is Asif Amin. I hope you are having an amazing day because I am having an amazing day. And if I am having an amazing day, you should be having an amazing, happy day. So, today, what I'm going to talk about is ODEs and its applications in automotive industries. Without further ado, let's begin. What am I going to talk about is what is ODE? What are the methods used to solve ODE? What are the applications of ODE? And why ODE is used in automotive industries? So let's begin with what is ODE. To begin with, a differential equation can be classified as an ordinary or partial differential equation, which depends on whether only ordinary derivatives are involved or partial derivatives are involved. The differential equation can also be classified as linear or nonlinear. The term ordinary is used in contrast with the term partial differential equation, which may be with respect to more than one independent variable. Mathematical modeling. What is mathematical modeling? It's basically the physical challenge that we come across when dealing with practical challenges and converting them to mathematical expressions in terms of variables, functions, equations, and so on. And then we interpret the results in terms of their physical terms. Types of ODEs. There are many types of ODEs, uncountable types of ODEs. So here are a few like separable ODEs, homogeneous ODEs, exact ODEs, linear ODEs, second order ODEs, Laplace equations, and moving on, how do we solve ODE? To solve ODEs, first the ODE should be separable, which is dy over dx equals u is basically a function of x and v is a function of y. So rearranging them, we get v 1 over vy times dy equals ux times dx. Then integrating both the sides, we will get the equation. And if the ODE is homogeneous, it is reduced to separable form, which is dy over dx equals m is a function in terms of x and y over n is a function in terms of x and y. For exact ODEs, du equals m times dx plus n times dy, and we do the partial derivative of m with respect to y, and if the partial derivative of m with respect to y is equals to partial derivative of n with respect to x is equal, then and only then we can say that the ODE is exact. Moving on, linear ODEs. Linear ODEs, the general solution is given by y prime plus p of x times y equals r of x. And the first order ODE is said to be linear if it is written in this form only, where p of x is a function of x. First order ODE is said to be homogeneous if r of x equals to 0. And if r of x is not equals to 0, then this linear ODE is said to be non-homogeneous. One of the most crucial equations in the ODE is Bernoulli equation. This is Mr. Bernoulli who invented the most important equation y prime plus p of x times y equals g of x times y to the power a. If a equals 0 or a equals 1, equation 1 is said to be linear, otherwise it won't be a linear equation. Substituting u of x equals y of y, a function of x to the power 1 minus a, and substituting y prime and simplifying it, we will simply get u prime plus 1 minus a times p into u equals 1 minus a times g. Moving on to the second order ODEs, these are the most important ODEs as it has to deal with the applications in mechanical and engineering applications with respect to vibrations, wave motions, and heat conductions, and etc. A linear second order ODE is given by y prime plus p of x, y prime plus q of x, y equals r of x, where p of x, qx, q of x, and r of x is a function of x. Homogeneous ODE with constant coefficients has basically three cases. It is classified into three cases: case 1, case 2, and case 3. Case 1 is basically having distinct real roots, case 2 is basically having real double roots, and case 3 has complex conjugate roots. Each of them has their own general solution respectively given in the table shown. Moving on to applications of ODE. Are you bored yet, miss? Because this is where the deepest secret lies. The applications, there are several applications where we use ODEs in modeling and applications of various components and subcomponents, which includes mechanical systems, electrical systems, hydraulic systems, the behavior of these systems, or a rate of change of a variable with another variable. We can determine it with ODEs. So over here we have mechanical applications. The as we were assigned to the automotive industry part, so it falls under the mechanical category. So over here we can see a car, and a car that is a driver is driving the car, and when he is moving on a free road, he accelerates the car to increase its speed, which causes a traction force to build up, and this force is given by F, where m is the mass of the vehicle and v is the velocity of the vehicle. From Newton's law of motion, F equals to ma. We know that F is the traction force, m is the mass of the vehicle, and a is the acceleration of the vehicle. Now the question you might ask, miss, is where is the differential equation? Now, we know that acceleration is given by the rate of change of velocity, right? So we can say that A equals dv over dt, where v is the velocity of the vehicle and dv over dt is the acceleration of the vehicle. Now, if we substitute it in Newton's law of motion, we get F equals m times dv over dt. And at a specific point, if we want to find out, the equation can be written as f of t equals m times dv over dt. Rearranging it, we get this equation. dv over dt equals f of t over m. Now, if we integrate both the sides, we get mv equals ft plus c. mv, what does this indicate? This indicates the Newton's second law, which is rate of change of momentum, and force is directly proportional to it. Moving on to the next example, we have a suspension system in a bike. As you can see in the diagram, here the mass m is the mass of the bike, and it is the spring constant, and the bike is moving. So let's see in the next diagram, the mass and spring, we could consider it as a spring mass system where the m- the downward force is going to be the weight, and the upward force is going to be the spring force, which is F equals to kx, and the weight is W equals mg. Now, as I have shown, the upward force is the spring force, and the downward force is weight. So the sum of forces in the y direction is given by W minus F, which is basically equals to 0. So weight is equals to spring force, we can say. Therefore, mg is equals to kx. And when the spring is displaced by a distance of y, it is given by k times h plus y as a function of t, since at time t it was displaced, and the weight is given by mg. Writing the balanced equation, we get f of t equals m times d square. This d square y times t over dt squared indicates that the distance is being derived once, which is the velocity, and the velocity is being derived again, which will give us the acceleration. And the new equation we get by adding the sum of forces is minus m times d square y t over dt square minus k times h plus y t plus mg is equals to 0, since the sum of upward forces is equals to sum of the downward forces. And from the above equation, we have seen that mg was equals to kx. And now, substituting it, we get m times d square y over t by dt square plus ky t equals to 0, which is in the form of an ODE and is second order. Engineers solve these ODEs to determine the hardness or the stiffness, as you can say, of the suspension, which determines the bumpiness on the road, or basically the dampness, how damp the suspension can get, whether damped, undamped, or critically damped. So here are the references that I've used, which is basically the lecture notes of yours and a single website, X Engineers, and it really helped me a lot. And thank you, Miss, for staying with me till the end. See you again. Bye bye.